The broadcast is now starting. All attendees are in listen-only mode.
All right, Paul, you can jump right in.
Good afternoon, everybody, and my name is Paul Brankleon. I am the Director of Research, Education Technology here at the North American Die Casting Association. Today, we are going to be going through Just Ask Paul for a second episode of additional questions. So let's get right into some of the questions. So I've got several questions today. This first question is, what is the state of additive manufacturing worldwide, and how does the United States compare to other countries? So first off, worldwide, in 2019, pre-coronavirus, the additive manufacturing did $10 billion in market growth for 2019. The initial analysis in 2020 was that it was going to increase. We're going to have to wait and see where this really goes. So from the 2019 data, I found several graphs and maps. This is a map of the world, and it's showing the regional growth rates, high being the Asian countries, medium growth being North America and Europe, and low being the African continent and South America. So the United States, moving forward, they're saying is going to be in the mid-range of growth. This is a graph showing additive manufacturing in 2018, 2019, and this is in billions of dollars. And this is different additive segments. So this is hardware, materials, services, and software. And in 2019, it just passed $10 billion. The expectation in growth from 2019 to 2025 is going to $32 billion, and by 2029, surpassing $53 billion in growth. So we've got a tremendous growth curve in additive moving on. So how does the United States compare to this? Well, in North America and Europe, they're the two largest regions for additive manufacturing. North America has 35% of the installed AM systems. Despite the leading position that the United States is in right now, the United States is at great risk of losing ground to the Asian countries and to the United Kingdom and Germany. So South Korea, China, England, and Germany are seeing also great growth in this. And if the US doesn't stay on top of this, it's not going to be the largest additive manufacturing center in the world. NADCA has several research projects that are focused on additive manufacturing. We have Worcester Polytechnic, Purdue University, Ryobi, Colorado School of Mines. Each one of these are projects that have goals and objectives and research PIs that are focused on die casting applications. For die casters that are listening to this webinar, if you're not using additive today, you need to be. Additive manufacturing, for the die casters that are seeing great returns, great increase in tool life, and reduction of scrap due to this. There's several additive projects that if anybody wants to email me, I can provide you the links to those so you can see firsthand what the applications are and what some of the savings that they're seeing. So there's a lot of applications today, and additive needs to be part of the die casting market. I've also included a website here, and there's a lot of additional worldwide information on additive manufacturing contained inside this website. Moving on to the next question. This is a plant-related question. So we have a leak test requirement on one of our castings. Is there a common mechanism within die casting that causes a leak path to grow over time? We have struggled with castings that pass the specification originally, fail at our customer, and then also fail when they send them back to be rechecked. What are the potential factors that come into play here? So let's break down leak testing. Let's talk about leak testing. So my experience with leak testing is that we have several different types of castings and several different methods of leak testing castings. The first two and the two most popular methods are going to be water or bubble check. So taking the casting located on the fixture, clamping it into that fixture, dunking the casting underwater at some pressure, and then pressurizing that casting. Now, I've also done that same pressurization with helium, much smaller molecule than air. So you can use air or you can use helium. When you pressurize those, you've got to make sure that you've got good protection for your employees in case the casting lets loose. But with the smaller molecule, you're going to see much higher leak rates. So helium versus air. So that's the water bubble check. And then the other type of leak decay or leak mechanism is going to be pressure decay. And this is dealing with a known leak rate. So with this type of leak testing equipment, you've got to have either a casting or a master part that you put in there, and it's got a calibrated leak unit on it. So it has a calibrated leak device, and you then check that unit every day and verify that it's measuring the same leak rate. Each one of these leak methods has their own concerns. Bubble leak testers, it can be masked by water quality, operator experience, clamping, sealing. So there's a lot of different things for bubble leak testers that are going to give us false positives. On the pressure decay, the allowed leak rate can be affected by the temperature. Temperature is extremely important. Hot castings check differently than cold castings. The dryness of a casting. So if you're using a pressure decay and the casting just came out of a machining center and it still has wetness on it, that wetness from the machining operation can mask the leakers. And then the calibration of the leak decay equipment. So how often are you calibrating? Are you checking known leakers to validate the equipment? So those two different types of leak checks can be done. So the other comment was, what over time can affect the potential leak rate? Well, castings do continue to shrink or creep, for up to 30 days. And if it was zinc, it'd be, for a year. But for aluminum, typically 30 days. After that aging occurs, we do see some reduction in mass or some shrink that occurs. That could affect leakers. I wouldn't say that's probably a real path. More than likely, it's either the temperature or if there's fluid or water or oil on the casting, that can also mask leakers. So as those fluids or oils evaporate, they either solidify on the surface or they evaporate and go away. They could create or open up a leak path that was blocked previously. Now, as a side note, anybody doing leak check, I think pretty much knows that impregnation is a way to save castings that previously leaked. It's not 100% cure, but it can improve the overall throughput of the castings. So recommendations would be to make sure the castings are room temperature, they're not hot. Once again, hot castings or cold castings can affect the overall leak ability, and then make sure that the castings are clean. Any waters or oils need to be removed. If it's a dunk tester, you got to check the seals and how the seals are sealing the casting, and the clamps to make sure that we're getting the same clamping every time. If you want a more stringent test, then go to a smaller molecule like helium. So you can do that safely, and it's going to give you a much higher leak rate because it's a much smaller molecule than air. This next question has to do with the cleanliness of metal. So the question is, the cleanliness of aluminum ingot can be measured by the prefill PODFA machine. How can inclusions be quantified and measured in an aluminum for structural components, for example, on a shock tower? So first off, let's clarify what this means. For clarification, the PODFA method provides information on inclusions in molten alloys. So we can take molten alloys and we can check them using this pressure filtration melt cleanliness analyzer, and we can determine the amount of inclusions and the type of inclusions that are inside our metal. It's typically for molten metal producers. For die casters, any inclusions that are going to be in the castings, especially for structural castings, are going to lead to reduction of mechanical properties, tensile yield, elongation. So if we have inclusions, we're going to see a reduction of mechanicals. The best practice that's available today is to degas and to flux the material. You can either use rotary injection flux, which is what I would recommend, or you can cast and work the flux in. But in either case, you're using flux to either remelt those inclusions back into the molten metal or to remove them and have them float to the surface so they can be skimmed off. Filtration can also be added, filtration between your furnace and either your launder system or your bull ladle. So you're going through a filter, and from that filtered material then is going to also remove any inclusions or remove some inclusions. So preventing the inclusions from moving from the melt downstream to the casting operation is probably one of the best practices. Understanding what those inclusions are using the PODFA or the prefill is a way to tell you where the inclusions are coming from. But actually removing those inclusions is probably the best method. The type of flux that a die caster can use is die caster dependent. For each process, there's a unique process and a flux that will improve and remove inclusions in the molten metal. Inclusions do not apply to structural die casters only. Any die casting that has inclusions, can exhibit reduction of mechanical properties. So whether it's the structural die casting or standard die casting, if you need uniform mechanical properties, then you can use flux and degassing methods to improve the casting quality. The next question is, we use a 100-gallon water tank to quench aluminum die castings. We use soft water to fill the tank, and we use a pump to circulate the water through a tube heat exchanger. The problem is the heat exchanger and tank surfaces become built up with a slime, a gray material on the areas that come in contact with the quench water. The heat exchanger will clog up and reduce the circulation and flow, causing the water temperature to rise and increase unplanned downtime to clean the system. What is the best practice to reduce downtime and the excessive temperatures? So let's talk about quench tanks. So with the quench tank, you've got a couple items: temperature and water quality. So let's divide these into a couple pieces. First off, with the temperature, we're concerned about the casting quality, the quench temperature, and the trim temperatures. So if the casting is extremely hot coming out of the quench tank, that's going to affect trim shear, the trimming operation. So we want that temperature to be uniform or a lower temperature. And frankly, for several years, I ran a casting. It was a 15-pound gate running 90 shots an hour with ejection temperatures right around 550 degrees Fahrenheit. With a standard quench tank, I had a very similar setup with a heat exchanger on the tank, and frankly, it was only 2 to 3 hours after starting the production operation that the water would be near boiling. So we tried several solutions, and I've got a picture of one solution on the screen here where we actually used an external heat exchanger, the kind that was described with a tube standard heat exchanger, along with a plate heat exchanger. So we had a plate heat exchanger in the quench tank, and we had a tube heat exchanger, and then we had to actually go to some water treatment, which I'll talk about here in a minute, to treat the water and then actually keep the water cooler. Another thing that we did was we ended up bubbling air through the tank to add turbulence. So we put a water line down on the bottom. It was basically a pipe with holes in it like a manifold hooked up to an air line. So we would have a constant stream of bubbles coming up through the water. That water then increases the overall surface contact with the surrounding air, lowering the water temperature. So it's a way to externally remove heat along with the heat exchangers that are tied to the system. So we have temperature, and then we have water quality. And that's frankly going to be growth of bacterial materials inside the quench system. And that's what was mentioned here. So we've got microbes that are going to attack the cooling components, changing the performance of those components. Action to prevent that kind of contamination is going to be some sort of biocide or a quench solution that can be added. And there's several commercial quench solutions. And if you want, you can email me and I can get you some names of those solutions to be added to the quench system that will then overall clean and keep that biological contaminant down. So some of the stuff you mentioned were those particles are going to plug the orifices. We get these paper-like particles in the transport lines. And frankly, we get something like this on the right, where our heat exchanger is just full of this microbiological material that's going to foul these tubes and then reduce our cooling. So we get this microbial contamination, and these biological organisms like to grow in those warm fluids. Another solution would also be to put an ozonator. So an ozonator is used in coolant recovery systems. It's used in hot tubs. It's used wherever, you can add ozone to a water system and bubble ozone through that water, and then it's going to act as a biocide also, where it's going to kill any bacteria that's in the water. So you can add an ozonator to the side of a quench tank, and they're just small devices, and they will just create ozone and then pump it into the quench tank. So there are several things that you can do to eliminate or reduce that bacteria and algae growth. The fifth question is there any updated calculation for the gate area relative to the part weight and shape for structural castings versus traditional component castings? So what we're talking about here is when we gate something, can we calculate the gate area for a structural casting versus a standard die cast process? Right now, the gating equation has not been changed to account for high vacuum applications. So when we use a high vacuum process, the standard is to gate the short distance of the casting and to gate the entire allowable area. So let's examine what that is. So here's a die cast die. We can see the part impression here in the center with the runner system and the gate. So we're gating across the short distance. We have multiple vacuums, and we have a seal that goes around the perimeter of the casting. So we gate the entire available distance, and we gate the short direction. This is typical to structural die castings today. And then we create a vacuum in multiple points, and we measure that vacuum in the casting. So we want to be between 20 and 100, 150 millibars, definitely under 500 millibars. Otherwise, we're going to have trapped gases inside the casting. So we're having the die cast die. We're gating this short distance, and we can see that. And then once again, we have multiple vacuums and a seal around the perimeter. Today, there is not a gating equation to say how much gate area is optimal for this type of a casting process. Now, with this casting process, my own experience has shown the error is minimal. minimal to the point that we can heat treat the casting, and we're going to get no blistering as long as we have great vacuum and removal of the air during the casting process. The current gating equation was updated in 2016 by Dr. Al Miller from The Ohio State University. At this point in time, additional work has not been planned to look at the gating equation for high vacuum applications. One other comment is that even though we don't have a straight calculation for the gate area or allowable gate area for high vacuum applications, the critical slow shot, fast shot length, fast shot transition, tensification, and biscuit collapse are all still very critical parameters to standard die casting and to structural die casting. My point is that all of the other process parameters are still very pertinent to the die cast process regardless of what we're making using the high pressure die cast process. Even though we're putting as much gate area in as possible over the short distance of the casting, the high vacuum is making up for that during the process. Our next question is, what is NATCA's opinion on composite toe versus steel toe boots? So I've got a lot of stuff on this screen, and basically this boils down to this first section are the ASTM and ANSI standard that govern protective footwear. This footwear undergoes some testing to test it for impact resistant to specified weights. And the composite safety shoe is just as the name suggests, instead of steel, they're using composite toe shoe or composite material in the toe of the shoe. And this composite material is then tested to these same standards. The standards of requirements for shoe or for this type of PPE is impact resistance, compressor resistance, metatarsal protection, conductive protection, electrical hazard resistance, puncture resistant, and static dissipative properties. So these are the tests for the footwear that are undergone. The bottom line for this type of footwear, is that it needs to be spelled out by the individual company. As the testing suggests, if a composite shoe can meet the OSHA requirements, and the requirements are spelled out in 1910-132 and 1910-136, then OSHA is going to be satisfied that these shoes are going to meet the requirements. So once again, bottom line is they're both going to work, but OSHA has a whole lot more data on the steel-toed shoes, so it may be safer to use steel in case there's an accident. My next question is, do we have an Excel spreadsheet for die thermal calculations? The thermal heat transfer is taught in our die design course, EC 506. This course takes into account the thermal input into each section of casting, and then how much the biscuit, the overflows, the casting. The input is calculated, and then the waterline length and depth is determined for each section of the gate, casting, and the overflows. So when we have our castings, we're designing these in CAD. We're then designing in the water systems, and we have the ability to calculate the waterline length and then each individual waterline depth for the biscuit area, the runner, the gate, and then all the sections of the die casting. So this is taught in our EC 506. NATCA does have this spreadsheet. Now we have two different thermal calculations. We have it's a very detailed heat thermal transfer equation that's detailed in the book, and I could walk somebody through how that's done. Or we have this thermal design, which is a simple spreadsheet for calculating the water line. So we can calculate at the biscuit, at the runner system, and then for each one of the sections of the casting. And what we're calculating is the distance each cooling line is for aluminum, zinc, and magnesium, and what's the distance in inches and in millimeters, and what's the length of each individual cooling line. So how long that cooling line is for aluminum, for zinc, and magnesium. And then this is all based on the water line size. So we have a 1/4 inch, 3/8, 700 thousandths, and basically that's based on the gallons per minute. So we do have a spreadsheet. Anybody that wants a spreadsheet can contact me. Follow-up material on this is the E506, which is designing die-cast dies. All of the equations, both the simple method and the standard heat flow method, are spelled out in this book in the thermal analysis section. So those are all the questions that I had for today. I've got a few more questions, and if anybody has additional questions or things that you'd like answered, please email those in, and I can add this to our next edition. So I'd like to open this up to any questions.
Thanks, Paul. So as Paul said, we're going to open it up for some questions. There are a couple ways that you can ask questions. Within your control panel, there is a text box. If you click within the text box, type your question in and hit send, we'll get that in on our end. The next thing that you can do is if you have a mic or you are calling in on a phone, you can click that hand icon. We will go ahead, call on you and unmute you, and you can ask your question out loud. You can always email us at NADCA. There is also a landing page now on our website that has the recording of the first broadcast and will contain the recording of the second broadcast as well as a link to our ongoing question page where you can submit any additional questions you might have. If you would like to just email them to us, you can do that as well. But the question page is always running. So if you just, something pops in your head one day and you just want to jot it down and shoot it over to us, we will be happy to answer that during our next episode. So with that, we're going to hang out on the line and see if anything comes through. If you had any follow-up or would like to have a little bit of a discussion back and forth with Paul right now on anything that you have a question about, we would be happy to try and facilitate that. All right, we don't want to keep anybody on the line any longer than we have to. So if you're in the process of typing something in, if you could click that hand icon, that will let me know that you're typing something, and we should hang out on the line while that comes through. Again, Paul's email address is up on the screen. Jot that down, and feel free to reach out and contact us with any questions you might have.
So the question is, how did Paul get into the die-cast business?
I like it.
So this is a long time ago. I actually started die casting when I was 15 at a company called SPX. So we were allowed to start casting and actually turned 16 that summer. I then worked as a die caster for summers through my high school years and then through college, and obviously stayed in die casting all the way to now. been primarily in engineering and engineering related functions for die casting.
I'm not gonna lie, Paul, I kind of wish you had a slideshow to show everybody, like Paul casting throughout the years. I think
That'd be nice.
yeah.
Running a die cast machine. We do have another question. What do you think the future challenges of die casting within the next 5 years? You know, when additive manufacturing came out several years ago, everybody went, "Oh, it's just a matter of time before everything's going to be printed." Well, I don't think additive is going to take over die casting. It may take over some aspects of die casting, some low volume, you know, direct component items. We're going to see a shift in the market in automotive. Automotive is the largest single user of die castings today. And we're going to see a shift from standard combustion engines to electric vehicles at some point. You know, with today's gas prices, frankly, where they're at today is rather stunning. It's not going to facilitate that shift at a rate that everybody thinks it's going to. So the combustion engine, I think, is here for quite a bit longer to stay. As long as the combustion engine is here, we're going to have those castings. We're going to have developments in structural. So OEMs are going to ask more of the casting, of the aluminum alloys. So I see us moving more into technical alloys. We're still going to have a lot of the standard stuff that's being produced. So die castings are used in automotive. They're used in buildings. They're used in appliances. You know, there's a lot of other usage. So in the next 5 years, I see that die casting is still going to be a very viable, very strong industry, as long as demand stays up in a post-corona world. So we're going to have to wait and see what that brings, as we all are working from our residences right now, and then soon to be getting back to work. So as long as the inputs to the automotive industry stay low, I think that we're going to see automotive castings for a lot of years to come. So I see it healthy. It's my bottom line.
All right, if you guys have additional questions, please send those in now. If you have any comments for Paul or anything that you'd like him to discuss at a later time, again, you can always reach out to him directly, or just send those questions through the question form that's available online as well. We'll just hang out just for a couple more moments here and see if anything else pops up. All right, I have no hands raised and no questions coming through. So with respect to time, I am going to call it for today. So again, thank you all for attending and participating today. You know where to find us if you have any additional questions. If you'd like to share this broadcast with anyone, it will be available on our website, the same place that the first episode was published, but I will go ahead and send over a copy of that link as well in case you have since lost it. So with that, everybody, thank you for attending today. And Paul, thank you again for helping us out with this episode of Just Ask Paul. So with that, thanks guys, and have a great rest of your day. Bye, everybody.